Hello students, I hope you are all getting well with the lessons. Today in this episode, we will be studying about continuous charge distribution. Actually, we are trying to prepare the background so that we can study the forthcoming topics, rather forthcoming important topic of Gauss law and its applications. So in order to understand Gauss law, Gauss theorem and its applications, first we have to understand about continuous charge distribution. So we will concentrate on the way charge can be found, like it can be in the form of discrete packets or discrete units, which we call discrete nature of charge, where the charge is able to maintain its individuality. Like we can say, when the charge is different and it has existence of its own, it can maintain its individuality, it can have its own existence, and it is different, segregated, and it is countable. In many other ways we can talk about it, because we have already seen this aspect in one of our previous episodes when we were talking about quantization of charge. But always we may not have discrete units. In most of the day-to-day life practical cases, we come across continuous charge distribution. Continuous charge distribution is a more practical way, because here infinite number of charges means many number of charges. Number is much greater than the size of the object on which they are placed. So infinite number of charges are closely packed and have minor space between them. When we are using these words closely packed, we are not talking in terms of some centimeters or millimeters. Yes, we are talking about a distance of micrometers or even maybe less than that. So you can understand 10 to the power minus 6 meters, such a small distance, they are having close pack arrangement and minor space between them. If such is the distribution of charge on any object, you say that the distribution is continuous charge distribution. And thus far we have been dealing with superposition principle and Coulomb's law. Using them, we could find out the electric field at a given point due to given number of charges. We had E1, E2 electric field due to first charge, then due to second charge, third charge, and so on. And by superposition principle and using vector rules, we could add all the electric fields or forces. But what if the number of charges are too many or infinite or uncountable? It is practically illogical or irrelevant. It becomes almost irrelevant and illogical to calculate electric field due to one charge and add them all, which will amount up to be an infinite number of electric fields. So illogical and impractical. So what should we do in such a situation? There we need the concept of continuous charge distribution, where we define as linear charge distribution, surface charge distribution and volume charge distribution. That makes that simplifies our situation and enables us to calculate electric field in a more simplified manner. So let's see what is continuous charge distribution, and we will see about linear, surface and volume charge distribution. First we will take into account linear charge distribution. From the word itself you are getting it, it is one-dimensional charge distribution, where charge is uniformly distributed over the length of the conductor. Over the entire length of the conductor, charge is uniformly distributed. You can see a figure over here, a uniformly distributed charge over the length of, you can say, a fine or a thin cylindrical length, and the charge is distributed, and this is introduced with a new letter, which is a Greek letter lambda. Till last year you might have used it for wavelength. Lambda here is charge per unit length. This letter will represent per unit length what is the charge. Lambda can be written mathematically as dq by dl. What is dq? small charge, and what is dl? Small length. This is small charge distributed over a small length, dq by dl. SI unit, charge represents coulombs, length is meters, so coulomb per meter. If we take, suppose that I have a length L of a conductor. I have a conductor of length L, and over this complete length L, charge Q is distributed. Q charge is over the entire length of the conductor. We have an observation point P at a distance r from the center of the length of the conductor. And suppose if we are interested in finding out the electric field over here, then we have to consider small length of the conductor. We have total length L, out of which we have considered small length of the conductor dl. And over this small length of the conductor, what will be the charge? Of course, the charge will be small dq, because q charge is over the entire length distributed. So, from here, small charge dq is the product of lambda into dl, charge per unit length into the small length. So, charge per unit length is lambda into dl. So, you get small charge is lambda dl. This is how we can get the expression for charge. And if we want to calculate electric field, there it is kq by r square, product of constant k into charge upon r square. There in place of charge we will use small charge dq, and you will get the expression for small electric field dE. And if you want to get total electric field, we will integrate dE. Small electric field will be integrated to get total electric field. That we will see in the forthcoming episodes. But right now we will move on to the next charge distribution, that is surface charge distribution. Next is surface charge distribution. From the word itself you can make out it is two-dimensional distribution of charge, which is represented again by a Greek letter sigma. We call it sigma. You are familiar with it. You might have used it for surface tension. So sigma represents charge per unit area. So mathematically it is dq upon dA. dq is small charge upon small area chosen. If suppose I have this complete area A, this complete sheet represents an area A, out of which we have chosen small area, we can call it dA. This is the small area chosen, which is dA. Then amount of charge in this small area, because this complete sheet is having an area A and this complete sheet has charge Q distributed over it uniformly. What is the charge found in a small area dA? It will be small charge dQ. Sigma, that is charge per unit area, is dQ upon dA. As such, units come out to be charge. For charge you have coulombs, and for dA, that is area, you have meter square. Similarly, third charge distribution is three-dimensional volume charge distribution. It is represented by a letter rho, Greek letter rho, generally used for representing density. So here it is representing volume charge distribution. So rho is charge per unit volume. Suppose we have a body of volume V. We have this body of volume V and it has a charge Q. Charge Q is distributed over the entire body. We are interested in small volume, three-dimensional space. So we have to calculate what is the charge present in this small volume of this complete body. That is charge distribution per unit volume dQ upon dV. Charge per unit volume. Units will be obviously, charge is represented by coulombs and dV will be meter cube, three-dimensional. So you have linear charge density lambda, which is dQ by dL. Surface charge density sigma, which is dQ by dA. And volume charge density, which is rho, which is represented by dQ by dV. So in order to find the electric field, suppose we have to find the electric field at any of these points, say P, due to this small sheet, then electric field, small electric field due to this small area which is having small charge dQ will be K small charge dQ upon R square. We can use this relation as D constant K dq upon r square. And if we want total electric field, we have to integrate small de. And we will have to integrate this whole term, where dq, we will replace it by sigma dA. dq will be replaced by sigma dA. And we will integrate this term to get complete electric field due to this entire sheet. Same method we can follow for linear charge as well as for volume charge. First, you have to calculate charge due to small length, then that is dE. Electric field due to small length is dE. Electric field due to small length can be integrated to get total electric field due to complete length. Similarly, electric field due to small volume dV can be calculated, and electric field due to entire volume can be calculated by integrating small electric field. So this is how we proceed. In the forthcoming episodes, we will be using these concepts in order to study Gauss theorem and its applications. Remember, stay connected, be regular, because now we are about to study something very, very important from this chapter. Very frequently asked questions from this chapter belong to this segment which we are about to study. Stay connected, stay tuned, stay healthy. All the best.